before going to the eigenvalue analysis beam, first let me discuss shortly how to get eigen solution for a matrix A. So we have learned that if A matrix is your square matrix, then we can find the eigenvalue and eigenvector of that matrix. Again, we have learned that eigenvector is one special vector. When it operates on a matrix, it is to give the same vector with some constant value. Okay, so eigenvector is a special vector when it operates on a matrix. When it operates on a special matrix, in a eigenvector is one special vector when it operates on a matrix, that is your square matrix. It gives the same eigenvectors or same vector with some constant value. Okay, now here you can see that if we have a matrix A, then we can solve that eigenvalue problem for a matrix in this way. So we'll put Ax is equal to lambda x, and then we'll take lambda x down left hand side, and then here we'll write in this equation. And since x is your non-zero vector, then this part should be 0, and then basically we're taking the determinant of it and we're making it 0, and then we find the lambda value. Once we find the lambda value, we put the lambda value again in this equation, and we try to find that eigenvector. So eigenvector is one special vector which operates on a matrix, and it is to give that same eigenvector. That means the vector do not change the direction, it's only magnitude is to change. So here you can see Ax is equal to lambda x, so it is the same vector. Okay, it is the same vector, only the magnitude of the vector is changed. So eigenvector is a one special vector when it operates in a square matrix. It is to give the same vector with some multiplication constant. Okay, so basically this is your eigen solution for a single matrix, or you can say for a single square matrix. This lambda, we used to say that eigenvalue, and if you take the square root of it, then we used to get that frequency. That frequency is coming as a radian, and we have to convert it to the hertz. Okay, so what we have learned, that how to solve a single matrix, okay, or eigenvalue solution. And one more thing, if we solve it, okay, then what we have to do, we have to write that for eigenvalue and eigenvector in this way. So each eigenvalue will have corresponding eigenvector. Okay, will have corresponding, or other we can say each eigenvector will have corresponding eigenvalue. Okay, each eigenvector will have corresponding eigenvalue. Now this part is fine since we are dealing with one matrix. Okay, now if you have a system, for example, if you have a beam, okay, if you have systems, for example, if you have a beam, in that case we have to deal with K matrix, we have to deal with mass matrix, and we have to deal with damping matrix. Okay, so our system equation or our structural problem basically related to stiffness matrix, mass matrix, and damping matrix. And how to get that solution for that? So what we'll try to see how basically we can go for eigenvalue analysis of a beam. Okay, so before going to that, what we'll see that how to write our dynamic equation of motion. So our dynamic equation of motion we write in terms of force. So mass into acceleration is a force, damping in the velocity is a force, K the stiffness into displacement is a force, and this is also one force vector. Basically, if some force is acting there, then how the beam is going to behave. In that case, we have to basically solve this equation. Now, what happens when you go for eigenvalue analysis? Okay, when you go for eigenvalue analysis, in that case, we need to consider that it is a free vibration case. So we need to consider it is a free vibration case. So in that case, what we need to write? We need to write the equation in this way: mx double dot or mu double dot plus cu dot plus kx is equal to, or ku is equal to 0. That means There's no force, it is free vibration. So free vibration means what basically we consider the free vibration. In the free vibration case, is to disturb that structure, okay, with a slight force, and then we leave it and we allow the structure to vibrate in its own motion. So basically we disturb structures. We can say we can pull it a little bit and leave it, okay. Or other you can say we used to disturb it and leave it so the structure can vibrate in its own. Okay, so that phenomena we can write in this form. Okay, mu double dot plus cu dot plus ku, that is equal to 0 force. Now here this is not sufficient for an engineer to get that solutions. We can solve it, but what happened here, if the damping term comes there, in that case we will get complex eigenvalue and eigenvector. Okay, if damping terms comes here, in that case we will have our complex eigenvalue and eigenvector. So what is the complex eigenvalue and eigenvector? That means whatever the eigenvalue we will get, that will be corresponding to complex valued function variable. So lambda will not be real value, that will be complex value. Lambda will be some value, okay, plus I into some value. Okay, so basically your eigenvalue will be complex number and eigenvector also will be complex number. Okay, now as the engineer, it's very difficult to deal with a complex number. So what we will to do? What we will consider? We will try to see how we can have a real valued solution. How we can get our eigenvalue as a real number and eigenvector also a real number. Okay, so to do that, what we will consider? We have to consider damping term as a 0. Now, if we consider free vibration case where force term is 0, we consider damping is 0. In that case, our equation of motion can write in this way. That is basically equation of a free vibrations. Okay. Now again, you just see still we are in the terms of u. That means still we are in the time domain. We have to convert the things in that frequency part. Okay. So what we will do? We will consider u, okay, as a function of phi sine omega t. Okay, we will consider u, okay, u as a phi sine omega t, where phi here basically we consider this is one factor that represent our mode shape or eigenvector. Then we'll see how it is coming. And omega term basically represent our frequency. Okay, so what we'll do, we'll put the value u in this equation and we'll see what basically we're getting. So here we'll put that u is equal to phi sine omega t, and if we take the double derivative of u and if we put it here, we'll get this equation. Okay. Now what we'll do, we'll take phi sine omega t common. Since we assume u, that is your phi sine omega t, okay, that basically we are assuming a non-zero quantity, non-zero in the sense neither omega is 0 nor this one is 0. So since this part u is non-zero quantity, so rest of the part should be 0. Okay, so rest of the part should be 0. So what we will do, basically we'll take the equation like this. We'll get the equation like this. Okay, and then also we can write in this way that your minus m omega square plus k, that is equal to 0. Okay, so now here you can see this is very similar, or otherwise you can write k minus omega square m, that is equal to 0, or determinant of this equal to 0. We can write in this way. Now here you can see this equation, your determinant of k minus omega square m, okay, equal to 0. It is very similar to the solution of a eigenvalue solution of a only one matrix. Okay, so here you can see if this m become identity matrix, then it will be the same equation. Okay, but normally what happens, this mass matrix will not have identity matrix. Okay, so what we'll do, we'll try to solve this equation and we'll get the solution. Okay, now if your K matrix is 2 by 2 or 3 by 3, In that case, we can solve it by hand calculations. Okay, but if matrix size become large, okay, if the degree of freedom of the system is large, in that case, our K matrix size also will be the same size. If you have the total 20 degree, in that case, we'll have, if you have beam, if we have a beam of 20 degree of freedoms, okay, then your K matrix size will be of 20 by 20. Okay, if you have a total degree of freedom as your 100, in that case, we'll have a stiffness matrix size of 100 by 100. So in that case, solution of this eigenvalue problem will be too much complex. We will not be able to do it by hand calculations. So we have to basically rely on some computer solution. Okay, so we'll see next how we can solve our beam problem, solve the beam problem in a computer. Okay, so here you just see how basically we can write stiffness matrix and mass matrix for a beam element. Okay, if we have a Euler-Bernoulli beam, in that case, our K matrix is to be like this. For each node, okay, for a beam, what happened? We used to consider each node will have a 2 degree freedom. Okay, so here 1 element, 2 element, 3 element, like that. We can have more number of elements. Okay, so each node will have 2 degree. One is corresponding to vertical degree, and another is corresponding to your theta. So depending on the how many number of node is there, we'll have total degree freedom. Okay, so if you know what is the total degree freedom, then your global stiffness matrix size will be of total degree freedom plus total degree freedom. Okay, for a single beam element, we'll have 4 by 4 size, because here 2 degree and here 2 degree, so there is total 4 degree. So this stiffness matrix will be of 4 by 4 size, and similarly mass matrix also will be 4 by 4 size for a single element. Okay, so this is the things we should know before jumping into our numerical solution. Now, if we want to assemble, so assemble in the sense, since if you have a more number of element, okay, if you have a more number of element, in that case, we have to assemble the stiffness matrix. So assemble in the sense, we have to define the stiffness matrix so that connectivity of this element can be maintained. Okay, so 1 element, 2 element, 3 element, 4 element. Okay, so like that, if you have 4 element, so here we have 1 degree, 2 degree, here will be 3 and 4, here is 5 and 6, here 7 and 8. So we have element 1, 2, 3. So basically total degree freedom is 3 element plus 3 plus 1 into 2. So basically 8 degree freedom we have for this beam problem. Now here, for this case, our global case size will be 8 by 8. Okay. Now next, we'll see that how we can obtain our stiffness matrix for a beam problem. Here, we just see we have considered a beam of 3, 4, 5 elements. So total number of node is 1, 2, 3, 4, 5, 6. Total number of node is 6. So we have 6 into 2 degree. So it will be 12 degree freedom. Stiffness matrix size will be 12 degree freedom. Okay. And here you can see that first element, for this first element, this is 1, 2, 3, 4. We are keeping the value of that first beam. Okay, that is basically 4 by 4 size. And since this node, that node number 2 is connected between 1 and 2. Okay, this node number 2 is connection between the 1 and 2. Then what happened? So you have to see which degree freedom, through which degree freedom it is connected. So here it is 1 and 2, it is 1 and 2, this is your 3 and 4, and this is your 5 and 6. Okay, so here you can see 3 and 4 degree basically play a role to connect between 1 and 2 element. Okay, so second stiffness matrix, that K2, which is again of 4 by 4 size, that you have to put from that third degree freedom. So because basically the same stiffness matrix, we're keeping it here because our element stiffness, our area and length are keeping constant. So basically we'll put the same value and we'll start from the third degree freedom, and we'll put from third degree freedom we'll start, and 1, 2, 3, 4. So like that till 4 again will fill. Okay. Now again we have to consider element 3. Again we have to see to which degree freedom it is connected. So here we have node number 1, node number 2, node number 3. So basically 5 and 6 degree freedom. Okay, through which basically element 2 and element 3 is connected. So again we have to see 1, 2, 3, 4, 5, 6. So basically we have to start again from that 5 by 5 degree, and you have to put the value 4 by 4 side from here. Okay, so if you keep on going like this, okay, you will get the global stiffness matrix of the size 12 by 12. Okay, now here you have to observe one thing, that your stiffness matrix, the global stiffness matrix is coming symmetric. Symmetric in the sense from the diagonal term, you can see it is coming symmetric. Okay, it should be symmetric. Okay, and symmetric in the sense this value and this value is same, this value and this value is same. So basically off diagonal term comes as symmetry. Okay, one more thing you have to observe, that this is very banded in nature. Banded in the sense that all the value are concentrated near the diagonal. So basically it has some band. So it is basically we are saying this is your banded. Okay, one more term you will get, that this stiffness matrix is sparse in nature. Sparse means you see a little bit away from the diagonal, that other term are 0. Okay, so basically you can see it is concentrated, all the value are concentrated in the middle zone, and the rest of the part of diagonal terms are 0. Okay, so we obtained few property, that our stiffness matrix is symmetric, it is banded in nature, and diagonal term you observe that all are coming positive. Okay. So these all are property indicating that our stiffness matrix may be semi-definite or definite. Okay, so it may be semi-definite in the sense, if you do not give any boundary condition, then our eigenvalue will be 0. Okay, so till now we do not provided any boundary conditions. Okay, so here we have to provide some boundary conditions. So boundary condition here we have, it is fixed. So v is 0 and theta is 0. So next we will see how we can apply the boundary condition. Okay, so if you do not provide the boundary condition, in that case our stiffness matrix will not be positive definite. Then we will get eigenvalue and eigenvector as a 0 values. Okay, that basically again indicating some rigidity motion of the beam. Obviously it will be rigidity because it is a simple beam and we do not have any boundary conditions. So this beam can freely translate along this direction, or it can translate along this directions, or it can basically rotate. At least 2 degree freedom will be there through which it can independently move, and freely it can move. And in that case we will not have any deformed geometry. Okay, so that is basically definition of the rigid body motion. Okay, so now how to apply the boundary conditions? There is various approach to apply the boundary conditions. One thing we just concentrate this degree freedom. Okay, basically first degree and second degree is basically restrained. Okay, it is restrained. So what we can say, that stiffness is very much high there. Stiffness is very much high there. Okay, now if we add some value the diagonal term, so that stiffness become high. Okay, that basically can replicate that fixed boundary conditions. If we add some value, okay, such a way that this term become very high in comparison to other off diagonal terms or other diagonal terms. Okay, if this value 1, 1, 1, 1 and 2, 2 value is sufficiently high in comparison to the other degree freedom value or other off diagonal term, in that case this stiffness basically will represent your fixed boundary conditions. Okay, so if we apply this type of boundary conditions, we can have a cantilever like boundary conditions, and we can have the solution. Okay, so here we have discussed that K matrix. Similarly, if we assemble for a stiffness mass matrix, then also we can get similar type of or mass matrix that also will be size of 12 by 12. Okay, so now we'll go for your MATLAB solution. We'll see how we can write the code in MATLAB and how we can get the solution and how to plot that eigenvalue eigenvector in MATLAB. So here you just see I have written that code. So here you just see what I have done. So here I have considered number of element 10. Okay, you can consider 5, then it will be easy for you if you consider 5 element. So if you consider 5, then next is that here how many degree of freedom is there. So total degree of freedom is how many degree of freedom is there. So basically 2 into 5 plus 2. So if you have 5 elements, total degree of freedom will be 12 by 12. Okay, so if you run it, you will get 12 by 12 size. So here you can see that your stiffness matrix here you can see this is your 12 by 12 stiffness matrix size. Similarly, you can have your mass matrix of 12 by 12. Okay. Sorry for that. With that our pen. Okay, so I have to deal with mouse. So this part is your depending on your how many number of element and how many degree of freedom. Okay. Now once we know how many degree of freedom is there, then we can define that how many, what should be the size, what should be the size of the stiffness matrix. Okay, what is the size of the stiffness matrix? So here our size of the stiffness matrix is 12 by 12. Okay, and this section below to this section here we have defined that property. Okay, material property and some geometry. So material property in the sense rho and E value and geometry basically B, D, and A. Okay, that's the thing we have obtained. Okay, now we have considered length of 1 meter. We have considered length of 1 meter. Okay, and we have defined the stiffness matrix. Okay, we have defined the half of the stiffness matrix. Okay, here you can see 1, 1, 1, 2 have defined. 2, 1 also should define, but we have defined half stiffness matrix, and then we take the symmetry of it, and from there we can define the full matrix. And for the mass matrix for an element, we also have defined that also size of 4 by 4. So each element, okay, for each element we will have a stiffness matrix of 4 by 4 and mass matrix of 4 by 4. Okay, now what have to do? We have to assemble the stiffness matrix so that we can have the global stiffness matrix. Okay, so for the 5 element, so there is total 6 node and there is total 12 degree freedom. So our global size will be 12 by 12. Global stiffness size will be 12 by 12. We have to assemble it. So here you can see how we have assembled. Here we have run 3 for loop. First is that number of element up to how many number of element we want to repeat the process. And here basically II and JJ we are writing that how to put this stiffness matrix, okay, the element stiffness matrix in the global one. Okay, so here you can see when number of element any is 1, in that case basically that our first element will fill that first stiffness matrix. Okay, so that will start with 1, 1 and that will end with 4 by 4. Similarly, if NE become, so now once we finish this one, so here you just see once we finish this one, now P become 2 and Q also become 2. P become 2 and Q also become 2. Okay, so when we consider that any second element, that time P is 2 and Q is 2. Okay, now when we consider second element, in that case our P plus II, that basically 1, that will be 3 and Q also 3. So basically first here it will fill the 3 by 3. Okay, with that your stiffness matrix of you can say the local stiffness matrix of 1, 1. So 1, 1 of the local element stiffness matrix filled with the 3, 3. So similar that thing we have obtained here. So 3, 3 basically it is filling first 1, 1 of the stiffness matrix filling the 3, 3. Okay, diagonal term. Okay, like that it will basically fill for other degree freedom. Okay, so here you just consider, okay, consider it and you just try to concentrate here and you try to look how basically if element changes, how basically we can assemble it. Okay, now here you can see that our stiffness matrix, you can see that our stiffness matrix is coming in terms of value of your 4 e to the power 5. Diagonal term if you consider here, diagonal term if you consider here, 4 e to the power 5 and your 5 e to the power 3 in that range. Okay, and since till now we do not have any boundary conditions, so we basically apply the boundary condition by increasing the stiffness in the magnitude of e to the power 10. So you can see that off diagonal terms, the magnitude is coming. Off diagonal term magnitude is coming. Magnitude is coming in the range of e to the power 5, e to the power 4 like that. Okay. I increase the stiffness for this term diagonal 1 and 2 to the range of e to the power 10. Okay, basically now we have enhanced the stiffness and it will behave like a fixed. Basically, this behave like a fixed beam or fixity of the beam will increase. Here you have to do some trial. If you change the e value, in that case, your that diagonal terms value will change. Okay, so that here you have to do some trial. You have to check whether it is about 10 or it is about 12 or it is about 15, which one, for which one you are getting constant frequency value. Okay, so this term here you have some role to play and you have to do some trial here. Okay, now till now we have basically obtained our global mass matrix and global stiffness matrix. Okay, now we can go for eigenvalue solution. Okay, so here we are writing that this line we are writing for eigenvalue solutions. Okay, evac basically your eigenvector, eval means eigenvalue, and if you write k eig in bracket k comma m, we will get eigenvalue and eigenvector. Okay, since eigenvalue is to come as your basically that eigenvalue basically your square of your frequency. So if you want to get the frequency, then you have to take the square root of it and you have to basically divide it by 2 pi if you want to convert that thing in a hertz. Okay, initially basically what I also to say that eigenvalue or frequency basically we are getting in terms of radian that you have to convert into the hertz. Okay, that you can do, but if you are well comfortable with your radian terms, then you can deal with that. Okay, now here this part what we are doing, we are trying to plot that eigenvector or here basically mode shapes. Now here you can see what we did for the beam. For the beam, if you want to see how the beam is deflecting, okay, so basically first mode will deflect like this. Okay, like this. So what basically we used to do, we used to see how this point basically translates vertically this direction. Okay, how this degree freedom, vertical degree freedom translates like this node translates like this. Okay, this node translates like basically we used to see at each node how the vertical degree freedom basically behaving, how the vertical degree freedom is behaving. Okay, again you have to see that we also have rotational degree freedom. Now, if you directly plot that eigenvector, whatever you are getting in the MATLAB, that will be combination of rotational degree freedom and your vertical degree freedom. Okay, so in that case, we will not able to get proper picture of that mode shapes. If you want to see the mode shapes, in that case, you have to see how only vertical degree freedom is behaving at each node. So basically, what we will do from that eigenvector, we have to take out only that we have to take out the values which is corresponding to vertical degree freedom and with a plot. Okay, the same thing we will do in the MATLAB. So here you can see we have taken that vertical degree freedom, the first degree freedom, we have taken the first degree. Okay, first degree of each node. Okay, and we'll basically take it in another vector and we'll plot it. Okay, so here you just see we have considered that first column and the second column. Okay, so if you see evac, so here you can see it have the size of 12 by 12. So what we have to do, we have to take it only this value and then third value and then fifth value like that. So here we have taken that value. Okay, so k is equal to I into 2 minus 1. So when is I is equal to 1, then k1 will be 1. If I is equal to 2, k will be 3 like that. Okay, so basically we have taken only value which is corresponding to the vertical degree freedom. Okay, now you have plotted it here. So this part is for only plotting in the MATLAB. So here we have plotted that first vector and I have plotted second vector and we have assigned some color, red color, line width, marker size, marker edge color, marker fill color, like that all the parameter we have given. here we have given the parameter, and this is the legend first mode for this one, second mode for this one, and then we have given some title, eigenvalue analysis of beam, all the things we have given, and then we have given that x level it is that node number, y level is the magnitude, okay, and then we have basically finished the code. Okay, now once you click it, you will get that our eigenvalue, that is your mode shapes, okay, mode shape means eigenvalue, not the eigenvalue, that eigenvector, okay, and we have taken that only vertical degree freedom and we have plotted. So first node, basically you can see it is like that, okay. So basically you can see if we allow the beam to vibrate, if you allow the beam to vibrate, it will vibrate in this way, either this side or this side, it will go like that way, okay. And this is our second mode. Now here you can see this shape is not smooth enough. So if you want to have a smooth shape, okay, in that case you have to increase number of node or number of element, or other way you can say number of degree freedom. Okay, if you increase number of element, in that case you will have a smooth mode shape here. Okay, so one more thing you also have to know, that we also have to perform our convergence study, because that is one parameter for the finite element model. Okay, so what we will do, we will increase that number of element, we will see how your eigenvalue is changing. So if you see that eigenvalue here, the first eigenvalue is coming 30.47 for the 5 number of element. Here it was our 5 element. Okay, for the 5 element, our eigenvalue, first eigenvalue was 30, second eigenvalue was 191. Okay, now I changed to 10 number of element, and we'll see what is our eigenvalue. So eigenvalue is now 30.46, it is 190. Now it is changing a little bit. Now here if you see that mode shape, okay, if you see the mode shape, you can see that now basically your mode shape is very smooth. Okay, so initially you can see first one it was like this. Okay, so basically first mode will be it will go either this side or this side. Okay, that is basically same thing, only that magnitude is changing. Okay, plus magnitude, minus magnitude, like that is changing, and this is our second mode. Okay, so similar way we can plot our higher up mode also. So these are the things are there for eigen solution of a beam. Okay, so initially we have discussed how to solve our dynamic equation motions, and if you want to solve for eigenvalue analysis, in that case we have to first consider free vibrations, and then you have to neglect the damping terms, then only we can have equation which is corresponding to free vibration equations, and then we'll assume some solution for that at phi sin omega t, and then we get a equation that is your k minus omega square m is equal to 0. Okay, that equation basically very similar to our eigenvalue solution of a beam. If mass matrix become identity matrix, in that case it will be the same matrix. Okay, if mass matrix is identity matrix, in that case it will be our same matrix, but mass matrix normally do not come as a identity matrix, so this will not be the same. So basically here it will have the mass into lambda terms or mass into omega square term, that will be there. Okay, and we have to solve it. Now again we have discussed that if our stiffness matrix, size of the stiffness matrix is small, in that case we can have our solution by hand calculation. If that number of degree freedom is large, if the size of the stiffness matrix is large, in that case our hand calculation will be too much difficult. In that case, our hand calculation will be too much difficult. We have to rely on computer solution. Here we have discussed how to get solution in MATLAB. Okay, so I'll try to put that code in that description part. You also can copy and paste it to get the solutions. I hope you get some idea. Thank you. Yes.